All right, guys. So this is our last video then in the hypothesis testing for between groups one-way ANOVA. When we left off last time, in the previous video, we had calculated the between groups ANOVA for our experiment comparing memory for positive, negative, and neutral images. We had found that we had a significant ANOVA, but we did not know where those differences lied. We talked about how, because of that, we needed to run a post-hoc test. So the point of this lecture is really to cover two types of tests, what are called a priori or planned comparisons versus the post hoc test. Post hoc means after the fact, a priori means before that, right? Beforehand. So let's start with what the ideal would be. Now, in any experiment, you're likely to have it somewhat theoretically driven. That is, you've read some existing literature that said something about human behavior or something about animal behavior, whatever you're interested in, and based on that reading, you've decided that your experiment is likely to show some evidence to modify or support that theory. And so because of that, you may have a very specific prediction in mind. So in the previous example, we may have a very specific prediction in mind about how memory for negative images will be better than memory for neutral images. That's something that's established well throughout the literature in almost every experiment where people compare the two. What's not so clear is whether or not memory for positive images would necessarily be better than memory for neutral images, or whether or not it would differ at all from memory for negative images. So we might have some individual comparisons within that say specifically how we would expect to see a difference between negative and neutral, and thus that could be something we would call a planned comparison. Unfortunately, we don't always have all of those planned out. Sometimes our data themselves tell us we need to go back and look at new comparisons we hadn't thought to be relevant to begin with. And so there's a little bit of a difference between whether or not we have theory driving our comparisons or simply comparing all the different things we see in our data or things that arise in our data that suggest they might be theoretically interesting. So with those that are theoretically planned, those that have a really good established background theory to justify a comparison, these are ones you can set up before you ever collect your experiment. Before you ever even finish designing it, potentially, you can say, based on what I know already, I'm going to want to compare memory for negative to memory for neutral. That then would be considered a planned or a priori comparison. It's based on your literature review, the extant theory that's out there in that literature. Now, the good thing about planned comparisons is that planned comparisons, when you run multiple comparisons, this does not inflate the risk of your type 1 error. Remember that if we were to run multiple t-tests by themselves with no theory to drive them, that we would have to add the p-value for each one, and we would quickly inflate the p-value or the overall risk of type 1 error in our entire experiment. Planned comparisons, because they are theoretically driven, they do not have this same effect on the overall risk of type 1 error. Because of that, planned comparisons are the ideal. And so whenever your theory is strong enough to predict these planned comparisons, it's good to set these up ahead of time. If you have them, then you can just run t-tests. Instead of having to run what we're going to show you as post-hoc tests, you can run individual t-tests like we have in the past and see whether one group differs from another group and use a p-value of 0.05. If you're a little worried, you want to make sure that you're controlling for any possible risk of type 1 error, you can always use a lower one or use what's called a Bonferroni correction to figure out what your p-value should be based on the number of comparisons you're making. But the good thing about planned comparisons is that you don't have to worry about the risk of type 1 error increasing. Sorry, my cat wants to join us again. In the event that you don't have a theoretically driven comparison, or that you want to run all the possible comparisons that could exist between the various groups in your experiment, then you have to run a post hoc test. And the most commonly used one, and in part because it's so easy to calculate, is what's called the Tukey's honestly significant difference. Okay? It determines whether or not you have differences between your groups by comparing the means in a numerator, one mean minus the other mean, and then it divides by a measure of standard error. So it's really a lot like the t-test, honestly. And because you're making multiple comparisons, you have to adjust for that risk of type 1 error in a post hoc test. The way it does so is essentially by comparing to a different distribution than the t-distribution. It uses a distribution of Tukey values, or Q values, these honestly significant difference values. Those critical values are corrected for these multiple comparisons. And so the honesty part about the honest significant difference is that we have corrected for that possibility of making 3, 4, 5, or 6 comparisons, and so that it doesn't inflate the risk of your type 1 error. So differences between a pair of means. Remember, posthoc tests are sometimes called pairwise comparisons, because if you have, say, 3 groups, you split them up into pairs, negative and neutral, neutral and positive, negative and positive, and you do each of those 3 pairwise comparisons. Divide each of those differences between means by a measure of standard error, and you have your Tukey's honestly significant difference, which, as I've already said, is very similar, almost identical to a t-test. That does mean, though, that we have some form of the 6 steps again, right? We have to do some variant of that. We need critical values, we need to compare to critical values, but thankfully, we've been doing the 6 steps for so long that it should be really easy at this point. So what's our formula? You'll see it sometimes written as HSD, other times just a lowercase q. Tukey's Q, or Tukey's HSD, is equal to the mean of sample 1 minus the mean of sample 2 divided by a measure of standard error, right? S sub m. Notice that mean 1, mean 2, those samples are whichever samples you happen to pick for that pairwise comparison. So it could be negative and neutral, it could be neutral and positive, or negative and positive, and it could go negative positive, or it could be positive negative. It doesn't matter which order you put them in. And so for that reason, we always use a plus minus sign in front of our critical value, right? Because it could have ended up positive or negative just depending on the order that you put them in. Notice how similar this is to the t-test formula, where we had sample 1 minus sample 2 divided by the standard error of the difference, right? So this is our independent samples t-test formula. They are, in essence, the same thing. The only difference is that we're going to have to calculate standard error slightly differently, and that we'll be comparing now to a distribution of Q values, not a distribution of T statistics or T values. Now, how do we calculate standard error? That's different depending on whether or not you had equal sample sizes or not. So just like our homoscedasticity test, we have 2 different rules depending on whether we have equal sample sizes or unequal sample sizes. If they're equal, and neither of our examples so far were equal, we would simply take the mean square within, which we can get right out of our source table, and divide by the sample size of whichever group you want to look at, since they're all the same. So let's say there were 6 people in each group. You take the mean square within, divide by 6, you take your square root, and you've got standard error. When you have unequal sample sizes, it's all basically the same, except that instead of dividing by n, the size of one of your groups, you divide by something called n prime. N prime works by taking the number of total groups. So in our previous example of negative, neutral, and positive, we had 3 groups. Divide then by the sum of 1 over the n for each individual group. So I believe in that example we had sample sizes of 6, 6, and 5 for our 3 groups. And so that would be a 3 over the sum of 1 over 6 plus 1 over 6 plus 1 over 5. What this step is attempting to do is, because your groups have unequal sample sizes, it's trying to find what's almost like an average sample size between them. So after that, you determine a critical value from the table. You compare that back to make a decision, and then you're done. You conclude whether or not that particular pairwise comparison was significant or not, and thus whether one group was significantly higher than that other group. So let's go back to our data for that memory for emotional pictures, and let's see how you would work that in the Tukey HSD. So remember our conclusion, our decision that we came to at the end of that experiment was that recall of negative, neutral, and positive pictures was different on average, right? Our F ratio of 17.97, P less than 0.05. Our question was, where are our differences, right? So before we do our individual comparisons, let's get our critical value that we need to compare our Q to. So that table of already stated calculated values again. Now we have a new table. This is at the very last page of the packet that I've given to you guys. You can find online. The Q statistic. Now note that there's one difference between the way the Q table is organized and the way the ANOVA table is organized. So in the ANOVA, we had the between groups degrees of freedom at the top, and then within groups degrees of freedom going down the individual rows. The Q, instead of listing between groups degrees of freedom, lists what they call K. K is the number of treatments or levels. So if the number of treatments of levels in our experiment is 3, because we have negative, neutral, and positive, then K is equal to 3. Notice that the relationship between K and between groups degrees of freedom is that between groups degrees of freedom is simply K minus 1. So if our degrees of freedom between was 2, our k is equal to 3. It's our 3 groups. So long explanation there, but that means we look at the column for 3, we look at the row for 14 for our within groups degrees of 14, and you find a critical value then of 3.7. Remember, this is a plus minus value to take care of whatever order you happen to put your pairwise comparisons in. Putting all that information then together, we've got a critical value, we've got all our information about the individual degrees of freedom, our total degrees of freedom, we've got our raw data, we've got our means for everything, we even have our source table. We have everything we had for that last experiment, or for that last particular example. So what do we need now moving forward? Well, essentially we know we're going to need mean square within. We know we're going to need to divide that by either n or n prime. So let's see how we do that step, right, to get that standard error. So we have unequal sample sizes here. We had 6, 6, and 5. And so in order to get standard error, which you can see at the bottom, standard error is equal to the square root of mean square within divided by n prime. We need to first figure out what n prime is, that average sample size. And so if you look to the formula above then, n prime is equal to the number of groups, which we know is 3, negative, neutral, and positive, divided by the sum of 1 over n for each of our individual groups. So that's a 3 in our numerator for the number of groups, divided by the sum of 1 over 6 for the number of individuals in the negative group, 1 over 6 for the number of individuals in the neutral group, and 1 over 5 for the 5 individuals in that positive group. This gives us a 3 over roughly 0.533, which gives us then an n prime of 5.625. So we now return down to that bottom set and plug in our mean square within from our source table. Our mean square within was 0.0064. Our n prime now was 5.625. Divide those through, take a square root of that result, and we have a standard error of 0.034. Okay? Remember, this would be even easier if we had equal sample sizes, because then instead of writing down this average sample size, we would just write whatever the sample size was and mean square within divided by that. So the last step is to run our Tukey test itself. All right, so we run 3 of them because we have 3 means, and we have to do the negative to the neutral, the negative to the positive, and then the neutral to the positive. So we've got all the information we need there. Tukey test negative neutral would be a 0.86 minus 0.61. We divide by the measure of standard error we just calculated, the 0.034, and our first test gives us a result of 7.35. Because this is greater than our critical value of 3.7, we would say that negative pictures were remembered differently from neutral, specifically that negative pictures were remembered better than neutral. We know it's better because they're 0.86 and neutral is 0.61. The next one, negative versus positive, 0.86 minus 0.634, divide again by that measure of standard error, and we get a 6.65. So just like before, this passes the critical value, and we would say that negative pictures were remembered more frequently, better than positive pictures. Finally, neutral versus positive, 0.61 minus 0.634. Divide that by our standard error of 0.034, and again, we now have a Tukey value, a Tukey statistic of negative 0.71. Negative 0.71 is considerably closer to 0 than our critical value of 3.7. Therefore, this one is not significant. This says then that memory for neutral and positive images do not differ from one another, which means that negative is better than neutral, better than positive, but that neutral and positive are not different from one another. And so the conclusion we would write after our initial ANOVA test, where we had written our sentence about finding differences and we list our F ratio, we would then write post hoc comparisons using the Tukey HSD test revealed that negative pictures were remembered better than either positive or neutral pictures, with no differences between the latter two. You can tweak that wording how you wish, but essentially conveying where the differences are. Note that I've also included in parentheses an italicized uppercase M and then the mean value for each of those groups where it was relevant in the sentence, so that your reader can not only see that there were differences, but also do a visual comparison of the size of those differences. Lastly, I said that when you have the post-hoc test, one of the reasons you're doing that instead of t-test is because you're trying to control for the risk of the inflation of type 1 error. Each post-hoc test controls for it slightly differently. The Tukey HSD we've seen. Another way of doing this is to essentially still run a t-test, but before you run it, you use a different value than 0.05. we saw that if you had run 3 t-tests with a 0.05, you'd be very quickly up at about a 0.15, a 15% risk of error. But what if you ran each of your t-tests at a 0.01? Then if you ran 3 of them, then that summed error would still only be a 3% risk of a type 1 error. That's essentially what the Bonferroni correction is attempting to do. It takes its own approach to controlling for the risk of type 1 error and the inflation that occurs, essentially by giving you a unique or different p-value you can use to test each of your comparisons. And so if we say that we had 3 comparisons because we had 3 means, like we did in our example, then when we ran each of our individual tests, we would use a Bonferroni correction and test it at a p-value of 0.017. Summed across, then, this would still stay below the 0.05, and we can be safely assured then that we are pretty close to the same level of risk we had before. Right? You can see that for a greater number of means and greater number of comparisons, your Bonferroni correction then gets smaller and smaller and smaller, to the point where if you had 7 means and 21 individual tests, you would be testing each of those at a p-value of 0.002. Again, the Bonferroni is just another way of correcting for the increase in the risk of type 1 error that occurs when we run multiple tests. So to summarize the between groups one-way ANOVA, first video introduced the idea of the ANOVA and why it's necessary, what differs between it and the t-test, and what the particular properties are of the ANOVA and the design itself. Part 2 gave a quick example of how to calculate the ANOVA that ran through a tangible example we could all think about between foreign graduate students weighting financial factors importantly when they came to the United States. Let us introduce concepts like degrees of freedom and sums of squares for each of these sort of new terms we have in ANOVA. Part 3 then gave a more detailed example of how to calculate the ANOVA using data from a study on memory for negative, neutral, and positive images. And then Part 4 finished up our video from Part 3 by taking our significant ANOVA result and seeing what happens next when we run a post-hoc test in order to determine where those particular differences lie. So after all 4 of these videos, you should be well sort of brought up to speed on how to run a between groups one-way ANOVA, which means you should now be able to tackle the homework assignment on between groups one-way ANOVA. Remember that on the exam, you will only be seeing a between groups one-way ANOVA in the calculation sections. You will get questions about other types of ANOVA that we will cover in other videos, but you will not be required to calculate the between groups one-way ANOVA. All right, thanks, guys. Talk to you next time.